All right. I should probably wait till later to say this, but I'm afraid if I wait, I'll forget to say it. So I had a question in my first class this morning. Are we having class on Tuesday? And the answer is yes. Okay. However, um, this sounds terrible to say, but I'm really serious about it. I would much rather you vote than come to class and not vote, okay? Because I'll record the section, I'll do whatever it takes. I want you to vote. So if you haven't already voted, which I hope you have, my wife and I have already voted, uh, I hope you're registered to vote. And if you are and haven't voted already, please, please vote on Tuesday. It is an incredibly important election, so please vote. The reason the question was asked before earlier this morning, it's my biggest class, and one of the students said her history instructor had said they have Tuesday off, no classes, and my guess, and this is just a guess here, he's probably working the polls, okay, because I know that some people are very, very keen on doing everything they can to help this election go smoothly, okay? So I'm guessing he may be working the polls. That's why he canceled class for Tuesday. He can't be there. But if you can, be in class. But if that's the only time that you have to vote, vote. Then get back to class as soon as you can. And even if you miss it, I'll try to record the class like I always do and post it on YouTube videos. If something screws up with the YouTube videos, I'll leave it out there from the last time I taught the course, which was last summer. It'll be there still, so you won't miss anything. Please vote, though. Please vote. All right. Any questions? All right. Where we left off last time is, I think, the top of page 120. I don't have a mark, so I think that's there. We're in Chapter 3, Determinants. We're in Section 3.2, Determinants and Elementary Operations, and that's what we were doing last time, and that's where we left off. So, any questions on anything before we get going today? Okay. Now, although Theorem 3.3, which we did last time, is stated in terms of elementary row operations, the theorem remains valid if you substitute the word column instead of row. Okay? Now, we haven't done this in any other context except determinants. Okay? So don't think that you can just go around and start substituting rows and columns. You can't. But when you're dealing with determinants, you can. Okay, so operations performed on the column rather than the rows are also called elementary column operations. And two matrices are column equivalent, just like we used to talk about row equivalent, when one can be obtained from any of your elementary row operations, column operations. Okay, here's a couple of examples. Now this only pertains to determinants, not to other things like solving systems of equations and stuff like that. So here we have a determinant. 2, 1, -3. 4, 0, 1. 0, 0, 2. Okay, that's a determinant. Now, remember the rules that we did before. The elementary row operations, you can either exchange two rows, multiply one row by a constant multiple, add to another row, or multiply or divide any row by a non-zero number. Okay, well, column operations work the same way too. Okay, now in this case, oh, here comes Jesus. Let me mark him here. Okay, we got 2/3 of the class, the top and the bottom of the alphabet. We're waiting for James. Hopefully he'll get here. And Jesus, we're in Chapter 3, Determinants, Section 3.2, Determinants in Elementary Operations. Notice they didn't say elementary row operations, just elementary operations. That's what we're talking about now, because for determinants and determinants only, you can now do either elementary row operations or elementary column operations. The same rules hold for both of them in determinant land, not in any other thing like solving for equations and stuff. You can't do this stuff. Okay, now if you look at this determinant you have here, that's a pretty easy determinant. Why do I say that? Because here you have a column 2 is all, it has 2 zeros in it. Row 3 has 2 zeros in it. That would be a pretty easy determinant to determine. But making it even easier, if you were to exchange these two columns, then you wind up with a triangular matrix, triangular determinant. All you have to do then is do the product of the diagonal entries. So what we do then, but remember, exchanging two rows or columns negates the determinant. So this would then be minus the determinant, and what we're going to do is exchange these two columns here. Okay, so now you have 1 to -3. It takes a little getting used to. 0, 4, 1, and 0, 0, 2. Okay, you'd have to build the minus sign out because anytime you exchange two rows, you negate it. Well, this is just simply a diagonal, upper triangular matrix. Any triangular matrix, all you do is multiply. So this will be -8. That's the determinant of that matrix. Pretty easy to do. Okay? Now, they didn't actually do it, they just showed how you did it. Okay? Let's do another one. Here's a determinant of a matrix. 2, 3, -5. 4, 1, 0. And -2, 4, -3. Okay. Now, this is a lot more complicated of a determinant, but you can still simplify. Nothing super easy to simplify, but you can do it. The easiest thing to do, notice that this column are all even numbers. They have a common factor. So what you can do is factor out that common value, 2 times 1, 3, -5, 2, 1, 0, and -1, 4, -3. Now, again, it's not a lot easier to do, but it reduces your number size pretty big time. Okay? That's for determinants only. If you're factoring out of a matrix, you have to factor out of every term in the matrix. You're not doing that. You're only factoring out of a row or a column. Okay? And that's what they get here. 2 times 1, 3, -5, 2, 1, 0, -1, 4, -3. Okay. Again, that's not particularly easy to take that determinant, but it's a 3 by 3. You could expand the first two rows and and do your down diagonals and up diagonals. So it could be done. They didn't figure out what it was. All they did was show you that you can do those elementary row operations. So, any questions on that? Now, I don't know. Let me clear my drawings here. Zoom is doing some weird things today. I've got two of you here, and I'm only seeing one name. so I wanted to make sure we hadn't lost Kira, that she wasn't waiting to get back in, but she's fine. But I only see Jesus's name here. Okay, don't know why. Yeah, I know you are. I just checked and saw. But why I'm only seeing one person at a time, whereas this morning's 2 classes I saw 4 or 5 people at a time. I'm only seeing 1 now, so I don't know why. Just wanted to check and make sure you hadn't gotten bumped out. Because with the storms last night, there was a lot of power outage. There was a lot of probably internet interruptions and things like this. So I wanted to make sure that you didn't get bumped and we're trying to get back in. All right. So let's move on to example 3. This is again on page 120. And this one you can go to larsonlinearalgebra.com to see an interactive version of this type of example. So here's what we're going to do. Find the determinant of this matrix A. Now I'm going to go on and do the determinant signal, okay? Just to keep from having to write a different step. -1, 2, 2, 3, -6, 4, 5, -10, -3. Now, not a particularly good looking, fun determinant to do, though it's not bad at all. But looking at it, seeing if there's anything you can do to make it a little bit simpler. There may be several things, but remember, look at both columns and rows. And what I see right off the top is that second column here, every element has a factor of 2. Okay? So the first thing I'm going to do is factor out a 2. So this is going to be 2 times the matrix, the determinant of -1, and you're factoring out of only the second column. That would be a 1, 2, 3, factoring out a 2 would be a -3, 4, only that column, okay? 5, -5, -3. Okay. Now, admittedly, that didn't help a lot, but it did help some, okay? Now, what you could do is other elementary row operations, like multiplying a row or a column by another value. Remember, that doesn't change anything about the determinant. So what we could do is do that, and we could eliminate this 1 and that 2, make zeros there, and that would make the whole process a lot easier. But you know, there's no real reason to do it. Let's just take this and do our expansion here to be a -1, 1, 2, -1, 1. This will be a 3, -3. Wait a minute. Time out. Time out, folks. I just noticed this. Look at this. This column is a multiple of that column. Anytime you have a column that's a multiple of another column, the determinant is 0. Done. Stop. You don't need to do anything else. This is completely not necessary. That's going to give you a 0 determinant. Anytime you have a row or a column that's a multiple of another row or another column, stop right there. You know, if you had noticed that here, if I had noticed that here, this column is exactly -2 times column 1. I could have stopped right there. But when I factored out the 2, it made it really more obvious. Okay, so that's example 3. Now, I'm not sure that's what they were trying to do, but you certainly could do it. They added, they didn't do what we did. They did elementary column operation. They did 2 times column 1 added to column 2, and they got a column of all zeros there, which gave us a 0 determinant. Okay. Now, there's a little blurb at the bottom of page 120 on linear algebra applied, and that's dealing with a game I used to play a lot. I haven't played it most lately, Sudoku. Okay? Really a fun game, deals with numbers, can be quite complicated, can be pretty easy, but it's a really fun game to play. It's linear algebra applied. Okay? Just right there. Potential paper topic there if you want to follow up on that. Okay, let's move on to page 121. Now, example 3 showed that when two columns of a matrix are scalar multiples of each other, just like two rows being scalar multiples, the determinant is automatically 0. That's one of 3 conditions that yield a determinant of 0. So I'm going to write these down. I'm going to clear this out of the way. And I think what I'll do is I'll type this one in. Not that my typing is all that good, but it's probably just easier to read. So let's go to the text mode here and do this. Okay, so I'm going to put aside my pad for a moment, and I think I'll hold my book in my lap. Okay, now, oh, here's James. Now we got a perfect attendance day. Way to go, team. Everybody's here. That means everybody's been here all week, and everybody was here all last week, except I wasn't because I had a treatment on Thursday. So anyway, y'all have been perfect attendance for at least 2 weeks now. Okay, way to go. James, we're on in chapter 3, determinants, section 3.2, determinants and elementary operations. And I noted here, notice it's not elementary row operations, elementary operations. Because with determinants and determinants only, you can do elementary row or elementary column operations. The rules are still the same. And this is what leading to page 121, theorem 3.4, top of the page. Okay, I'm going to try to type this in and see if this is easier to read. If, and it's not typing, okay, there we go. If A is a square matrix and any one of the conditions below is true, it's supposed to be a comma, okay, then the determinant of A. Now I'm going to try to type this in this way. The determinant of A is equal to 0. Okay? And here they are. 1 and entire row or column consists of zeros. Okay, that's 1. The second, 2 rows. Wait, 2 rows or columns are equal, or 3, any one of these, 1 row or column, okay, is a multiple of another row or column. Okay, those are the three conditions. If any one of those three are true, then you have the determinant of that matrix is 0. Okay, theorem 3.4. Now they do a little proof there. I'll let you take a look at the proof and see what you think is coming with that. Okay, I am still very low energy, still I'm sure quite anemic, even though I had probably the best night's sleep I've had in weeks last night. I still woke up exhausted. So hold on a minute, I'm going to add a little caffeine and sugar here and see if I can improve a little bit. Sorry about that. Now they do say at the bottom, sort of near the middle of the page, top half of the bottom of the page, do not conclude, however, that theorem 3.4, which I just typed here, gives the only conditions that produce a zero determinant. This theorem is often used indirectly. That is, you may begin with a matrix that does not satisfy any of these conditions listed here, but when you do your elementary row or column operations, you get a matrix that does fit the bill. Okay, and that's what example 4 will be doing. So I think what I'm going to do, does anyone need this up here a little bit longer? Okay, I'm going to clear this writing, and this time I will be using the pad. Here's example 4. Here is matrix A, and obviously I need my pen back. Okay, here we go. And we're going to do the determinant of A, and that will be the determinant of this matrix here. 1, 4, 1. 2, -1, 0. Excuse me. 0, 18. Going along very nicely till we hit that number, didn't we? 4. Okay. Now, what might you do to this? Now that's a 3 by 3, and you could just go on and expand, right? Repeat the first two columns, do your determinant that way. However, if you did something as simple as an elementary row operation here, get this 2 to become a 0, then you're going to make life a lot easier. Now you could have gotten this 4 to become a 0, and that would have worked too. I think those are your easy choices. You could get this 2 to become a 0 using a column operation here. That would have worked pretty nicely too. Okay, but it looks like to me the easiest thing would just be to do that. And remember, when you add a multiple of one row to another row, you do not change the determinant at all. So what we're going to do is -2 row 1 plus row 2. Okay, we're leaving row 1 alone. 1, 4, 1. -2 times 1 is -2 plus 2 is 0. -2 times 4 is -8 minus 1 is -9. And -2 times 1 is -2 plus 0 is -2. Okay? And then let's leave the bottom row alone. 0, 18, 4. Okay. Now, pause a moment. Looky here. The third row is -2 times the second row. Not obvious here. None of these rows are multiples of each other, but in this one it is. The third row is negative 2 times the second row. Negative 2 times 0 is 0, negative 2 times negative 9 is 18, and negative 2 times negative 4 is negative 2 is positive 4. You can stop right there. That determinant is 0. Done, because your reduced form there gave you one row being a multiple of another row. Okay? Any questions on that? I don't know if that's how they did it. That was example 4. Yep, that's exactly what they did. Okay? So the determinant is 0 as soon as you see a row or a column is a multiple of another row or a column, 0. All right. Let's move to page 122. It says in example 4, you could have obtained the matrix with a row of all zeros by performing an additional elementary row operation, multiplying column 3, row 2 by 2, adding it to row 3. That would have worked too. But why? I mean, as soon as you see that that one's a multiple of another, you got it knocked. Okay? You have now studied two methods for evaluating determinants. Of these, the method of using elementary row operations to reduce the matrix to a triangular form is usually faster than a strict cofactory expansion. Okay? If the matrix is large, that's a pain, but if the matrix is large, then the number of arithmetic operations needed for the cofactory expansion can be extremely large. And for that reason, most computer and calculator algorithms use a method involving elementary row or column operations. So the table that they show in the book here shows the maximum number of additions plus subtractions and multiplications plus divisions needed for each of the two methods for obtaining matrices, and they do order 3, 3 by 3, 5, 5 by 5, or 10, a 10 by 10. And we'll look at what happens with this. Now, I can't show this because my camera, I know it's working. You can probably see me, but I can't see it, so I can't hold this up. Well, I will hold it up, but I don't know if I've got it right. Can you see the table that I'm trying to illustrate there? Yes or no? Well, I'm not getting an answer, so I don't know if I'm in view or not. I wish I had my camera. I don't know why. My first two classes that did perfectly fine, now it's not. So I don't know why. But when you have a 3 by 3 matrix, and the only thing you can take determinants are square matrices, 3 by 3 matrix, cofactory expansion, you have a maximum of 5 additions or subtractions and 9 multiplication or divisions. So that's a total of 13. I'm sorry, 14. Okay? If you do row reductions first, you have a total of 18. So a 3 by 3, easier to do cofactory expansion. Go up by 2, 5 by 5. Look at that. Cofactory expansion jumps up to 324 cofactor operations. Doing row reductions, you're down at 84. Given a choice of 324 or 84, I'll go with 84 anytime. Go up to a 10 by 10 matrix. Look at your cofactory expansion now. That's something awfully close to 10 billion operations. I don't want to go there, okay? Whereas with row reductions, you can get by with just merely 669, okay? That's still a big number, but it's nothing like 10 billion, okay? So by all means, do your row reductions. Anything bigger than a 4x4 or larger. Anything larger than a 3x3, use your row reduction. In fact, the maximum number of additions alone for the cofactor expansion of an n by n matrix is on the order of n factorial minus 1. So if you had a 30 by 30 matrix, 30 factorial is approximately equal to 2.65 times 10 to the 32nd power. Okay, so even a relatively small 30 by 30 matrix would require an extremely large number of operations. If a computer could do 1 trillion operations per second, that's awfully fast, it could still take more than 22 trillion years to compute the determinant of that matrix using cofactor expansion. Yet row reduction would only take a fraction of a second, as opposed to 22 trillion years. Go for row reduction. Okay, so when evaluating a determinant by hand, you sometimes save steps by using elementary row or column operations to create a row or column having zeros in all but one position, then the cofactor expansion to reduce the order of the matrix by 1. The next two examples illustrate that approach. So I think what I'll do is clear my screen here. Oops. Why did it do that? My word, this is wacko. Okay. I don't know why it jumped to Blackboard. That was totally crazy. Here's example 5, bottom of page 122. Find the determinant of this matrix. Now this is a 3 by 3. You can do it either one of two ways. Okay. So here's the determinant of A. I'm not going to write the matrix, I'm going to write its determinant of negative 3, 5, 2, to negative 4, negative 1, negative 3, 0, 6. That was not looking very promising at all until we got to that last row, and now it looks a lot better. Okay, now what makes it look better? If you multiply the first column by 2, add it to the third column, you're going to get a row of zeros. So let's do that. I don't think I'll write it under here. 2 times column 1 plus column 3 is the new column 3. I should have written it over here. Okay, so let's do that. That doesn't change the determinant at all. So leave the first column alone. That's negative 3 to negative 3. Let me make sure I've copied that right. Yep. We're not fiddling with the second column. Leave that alone. 5, negative 4, 0. Make sure I copied that one right. Yep. Now let's do the column operation. Done. 2 times column 1, that would be negative 6 plus 2 would be a negative 4. 2 times 2 is 4 minus 1 would be 3. And 2 times a negative 3 would be a negative 6 plus 6 is 0. Okay, now that's going to be a lot easier to do. In fact, cofactor may be the way to go on that. So let's do it that way. I haven't been doing that. I usually would do an expansion. Let's just do it. Okay, so we're going to use the first row, third column. That's a minus 3. What's the sign of that position? Plus, minus, plus. So that's going to be a positive sign, but it's a negative 3, so that's going to be a negative 3 times the determinant that's left. 5 minus 4 minus 4, 3. And that's going to be pretty easy to do. minus 3 times 15 minus 16. That would be minus 3 times a minus 1, which is equal to 3. So the determinant of that is 3. Pretty easy to do. Does everybody see how to do it? Now they do the cofactor expansion, you know, the using the i's and j's. If you just count plus minus plus minus plus, you can eliminate that step. And we did get same answer they did. Okay? Any questions? Now, if that wasn't enough of an incentive, let's look at example 8. My word, this is a 5 by 5 matrix. I don't think we've done anything this aggressive before. So let's see if we can do the determinant of this matrix A, and this is going to be a 5 by 5. Now the hard part is making sure I get all the numbers right. 2, 0, 1, 3, negative 2. Negative 2, 1, 3, 2, 1. 3, 2, negative 1. 1, 0, negative 1. 2, 3. 3, negative 1. 2, 4, negative 3. And 1, 1, 3, 2, 0. Now, don't know what's going to be best here. I have a suspicion. What I look for first, and I hope I've copied it right. I hope y'all were paying attention and keeping me from making a dumb mistake here, because this is going to be a very hairy approach here. I think we're okay. All right. First thing I look for is the row or the column with the most zeros. And just a cursory glance here indicates column 2 has the most zeros. It has 2 zeros, and all the other entries are very simple, plus or minus 1. That's mine I'm going to do expansion on. So what I'm going to do here, the first step is going to do, using row 2, okay, I'm going to do row 2 plus row 4. Let's see what happens. Now this is determinant action here, not row reduction as per se. So, going to leave row 1 alone. 2, 0, 1, 3, negative 2. Why in the world that does that, I don't know. Negative 2. Okay. We're leaving row 2 alone. That's the one we're using. Negative 2, 1, 3, 2, minus 1. Okay. Row 3 stays the same. 1, 0, negative 1, 2, 3. Row 4 is the one we're changing, and that will be row 2 plus row 4. That will be a 1. Row 2 plus row 4 is a 0. Row 2 plus row 4 is a 5. Row 2 plus row 4 is a 6. And row 2 plus row 4 is a negative 4. Okay. Next one we want to do is now, I don't think it really matters here that much. The easier thing to do would be row 4 plus row 5. We don't usually do that, but it's still a legal thing to do. that will produce a 0 here too. So let's do row 4 plus row 5. A legal move, even though it's not what we usually do. So let's add those together, and you get a 4, you get a 0, you get a 5, you get a 6, and you get a -3. Okay, my writing isn't the best, but you know, there we have it. All right. Now, what will we do next? That determinant is going to be this 1 times wipe out this row and this column. I said this column and that row. Sorry, I said it backwards. Okay. This 1 is in position, a positive position. Plus, minus, plus. Plus, minus, plus. It's a positive position. So that's going to be, that determinant is going to be 1, which you don't even have to write down, times the determinant of what's left. Well, that would be 2, 1, 3, -2. 1 minus 1, 2, 3. 1, 5, 6, minus 4, and a 4, 5, 6, minus 3. All right. The big bad news here is we've lost all of our other zeros. Okay? So what might be the next thing to do? Well, looks like to me the next easy thing to do would be take this row here and with column operations get that to be a 0, that to be a 0, and that to be a 0. Okay? So we can forget about this 1 here. That's just multiplying by 1. Okay. So let's do column 1 plus column 2. Okay. That's going to be a pretty easy thing to do. That'll produce a 0 here. So this will be, leave column 1 alone, 2, 1, 1, 4. And we're going to add these two columns together. That gives us a 3, a 0, 6, and a 9. Okay. Next thing we're going to do, let's do minus, I'm going to do this one. 2 times column 2, add it to column 3. 2, column 2, add it to column 3. The reason I do that is just easier than doing a multiple. Okay, so let's do that. 2 times 1 is 2 plus 3 is 5. 2 times -1 is -2 plus 2 is 0. 2 times 5 is 10 plus 6 is 16. That's a big boo hiss. And 2 times 5 is 10 plus 6 is 16 again. All right, next thing, let's do 3 times column 2 plus column 4. 3 column 2 plus column 4. Okay, so that would be 3 times 1 is 3 minus 1 is minus 2 is 1. Minus 3 plus 3 is 0. Okay. 15 minus 4 is 11. And 15 minus 3 is 12. Okay. Now we're down to basically a 3 by 3. With one problem here, this position is a minus position. So that's going to be a minus 1 times this 3 by 3. 3, 5, 1, and I'm going to expand and make it a 3, 5. Now this isn't really a determinant, but it's pretty close. this will be a 6, a 16, 11, a 6, and a 16. Now that's awfully crowded. I hope you don't get those crossed up. A 9, a 16, a 12, a 9, and a 16. Okay, now don't forget your -1 there. Okay, let's do our down diagonals. I think I'm going to call on my calculator here because these are some pretty big numbers. Okay, so it's a -1 times, I hope I haven't made a dumb mistake here. Let me get my calculator brought up. And that's 3 times 16 times 12. 3 times 16 times 12. That's going to be 576. Yuck, big numbers. Where in the world is my key here? 576. Then I'm going to do my down diagonal here, and that I believe is a 55 times 9, I believe it is, plus 55 times 9 equal, okay, now I'm adding these together, so that's 1071 so far, plus my third down diagonal is gotten crossed up here, 3, okay, 1 times 6 times 16, okay, plus 6 times 16. I think it is. My writing sort of stinks, so I may be getting off here. So that gives me 1,167. Okay, now I'm going to clear, if I can. Okay, go and clear these construction lines here. Hopefully I've got that right. And put my drawing back in here. So this so far is a -1167. Okay, I multiplied by a -1. Now I'm going to do the minus times a minus is going to be a plus, because this was a minus sign out here. I'm going up here. So this is going to be 9 times 16 times 1. So I'm going to negate that and do a plus okay, I'm getting myself crossed up here. Yeah. So I think that's going to be a plus 9 times 16. So that's a minus 1023. And then we're going to do another plus, and this is a 16 times 11 times 3. So 16 times 11 times 3. That gets us to a 528. And then we're going to have a plus 12 times 30. I get 360. I don't know if that's what it turns out being. 360. Now let's see. No, it isn't. Okay, I botched something up here. Okay. Sorry about that. Okay. And unfortunately, see, we go to 12, 45. I don't have time to go back and see where I made my error here. But anyway, we did wound up. It's a big number, just not the same big number, okay? They did one more row reduction than we did. Let me see if mine even came out close to theirs. It doesn't look like it, okay? Because they did a different bent. But anyway, that's how you proceed, okay? I may have made a dumb mistake somewhere there, so hang with it and hopefully you can follow. It's just not worth taking class time to try to find the error. Sorry about that. Homework exercise, that finishes 3.2. Homework exercises here would involve any of the odds 1 through 19. They're all at Calc Chat. 21 or 23, they're both at Calc Chat. 25 through 35, they're all at Calc Chat. And then there's a true false 37, that should be at Calc Chat. It has 3 pieces to it. Then any of the odds 39 to 45, they should all be at Calc Chat. And 47 should be at Calc Chat. And that finishes section 3.2. So let's move. Any questions on 3.2? Okay. So let's move on to 3.3. 3.2 was determinants and elementary operations. 3.3, properties of determinants. Okay. So we'll be looking at the finding of the determinant of a matrix product and a scalar multiple of a matrix. We'll also look to find the determinant of an inverse matrix and recognize the equivalent conditions for a non-singular matrix. And finally, we'll find the determinant of the transpose of a matrix. So let's move directly into example 1 and do their example 1. Okay, we've got 10 minutes, no, 20 minutes. Let's see if we can get example 1 done easily in 20 minutes. Here's a matrix A. We're going to take the determinant of A. The determinant of A will be 1, -2, 2, 0, 3, 2, 1, 0, 1. Okay. Now since that's a 3 by 3, to me the easiest way is just expand it. 1, -2, 0, 3, and 1, 0. And this isn't really a determinant, but it's how we do it. So the determinant of A would be 3 minus 4 plus 0. Okay, that's the down diagonals. So let me erase this one, and this one, and do the up diagonals. That's a -6 because you're going upward. That's a 0, and that's a 0. So this looks like a -7. The determinant of matrix A is a -7. We're also going to do the determinant of matrix B. Matrix B is 2, 0, 1. 0 minus 1 minus 2. 3, 1, -2. Okay. I think that's all I need my book for, so I'm going to get that out of my lap for right now. Well, I might need it a little bit more. Let's do the determinant of B. Okay, well, what I forgot to do is expand it, so let's do that. Okay. Okay. 2, 0, 0, minus 1, 3, 1. Okay, now that's not really a determinant, but let's just pretend it is. This is 2 times 2 is 4, 0, 0. Okay, that was pretty easy. So let's erase those construction lines. And I erased more than I wanted to. I think that was a minus 1 there, wasn't it? Yeah. Okay, now let's do the up diagonals. And this would be a minus 3, but since it's up, that's going to be a plus 3. This one would be a plus 4. And this one would, of course, be a 0. So this gives us 8 plus 3 is 11. So determinant of A was negative 7. Determinant of B was positive 11. Now the next thing they say is find the determinant of AB. So the first thing we've got to do is multiply AB. So AB is going to be a 3 by 3. And what I'm going to do now, just to hopefully make things a little easier, if I can get my pen to show up, there it is. Okay, I'm going to go back to, come on, where are you? There you are. Okay, get rid of that, that, and I'm going to take away the expansion here. Okay, and we'll get rid of this, 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 and take away my expansion there. All right, now what we're going to do is determine what the product is. Okay, so I think what I'll do is make this go back looking like a matrix rather than a determinant. Like that looks like a matrix rather than a determinant, and probably lose the vertical bars here and here and here and here. Okay, so let's multiply. 3 by 3 by 3 by 3 is going to give us a 3 by 3. So first row, first column will be first row here by first column there. Okay, so that's going to be a 1 times 2 is 2, plus 0, plus 6. 2 plus 6 is 8. All right. First row, second column, first row here, second column there. So first row is going to be a 0, 2, minus 2. So I think that adds a 0. Okay. First row, third column, first row here, third column there. That's going to be a 1, plus 4 is 5, minus 4 is 1. Okay. Now, second row, first column, second row here, first column there. If I can get my pen to show up, there it is. That would be a 0, 0, 6. So that gives you a 6 there. Second row, second column, second row here, second column there would be a 0, minus 3, plus 2 be a minus 1. I hope. Pause just a moment. I'm about to feel like I'm about to pass out. I don't think it's that bad, but I feel pretty bad. Okay. Second row, Come on, pen, where are you? There it is. Second row, third column. Second row here, third column there. That would be a 0, minus 6, minus 4. I think that's a minus 10. Third row, first column. Third row here, first column there. That would be a 2, 0, 2 and 3 are 5. Third row, second column, that would be a 0, 0, 1. Third row, third column, that would be a 1, 0, minus 2, that would be a minus 1. I think. Okay. Now what we need to do is take the determinant of that matrix there. Okay. All right. Now how would we do that? Probably do our expansion. So I think what I'll do is those ugly lines I just put in there, I'm going to get rid of them and just expand here. 8, 0, 6, minus 1, 5, 1. Okay, now we'll do like a determinant here, and that would be what? That would be 8, down diagonal there, 0 there, plus 6. Up diagonal here would be a plus 5, plus 8, and here we have a 0. This doesn't look good. I may have done a mistake somewhere here. It looks like I did. The AB is 8, 4, 1. So obviously I made a mistake right here. So let's do first row, second column. First row here, second column there. That's a 0, plus 2, plus 2 is 4. I'm sorry, I did a minus 2. Okay. This is a 4. So that'll be a 4. I told you the old gray cells aren't working too well. Now, is that the only mistake? 8, 4, 1, 6 minus 1, minus 10. How did I do that one? So let's do the second row times the third column. It may be second row times third column. That would be a 0, minus 3, no, minus 6, minus 4. That was supposed to be a 0 there. 10. I think what happened, for some reason it checked out. Okay, so that was a 6 minus 1 minus 10, and then the third is 5, 1 minus 1. Okay, so let's go back. Sorry about that. Okay. Okay. Whew. All right, let's do our down diagonal here. That's still an 8. This is a, oh boy, that gets to be a big number, doesn't it? That's 20 times a negative 10 would be a negative 200. And then this will be a plus 6. Okay, now let's do our up diagonal. Alright, I'm about to lose it, folks. Sorry about this. I am so incredibly tired. Okay, let's do the up diagonal there. That's going to be a minus 5, which will be now a plus 5 because it's up diagonal. This will be a minus 80, but going up will be a plus 80. And then the third one is going to be, it would have been a minus 24, but it's going to be a plus 24. Okay. I'm going to use my calculator. I don't want to trust my brain any longer. Okay. It's not doing well. Okay. I'm going to start with the 200 there. Understand it is a minus, but I'm going to start as if it's a 200. And then I'm going to subtract an 8, subtract an 11, subtract 104. Hit equal. I get a 77, but because it was a minus 200, that's a minus 77, which is indeed what I expect it to be. If I can get my pen to show back up, minus 77. Now, let's take a look at something. Determinant of A, negative 7. Determinant of B is 11. Multiply them together, you get a minus 77. So sure enough, the rule is the determinant of a product of two vectors is the product of the determinants of those two vectors. Okay? And that's what they show here, and I think that's what they do here. Let's go to clear out my writing here, and let's see, I think I can type it in probably, okay, faster and better than I could writing it, or at least clearer for you to see. Here is theorem 3.5. Okay, if A and B are square matrices of order n, have to be the same size, then the determinant of A, and I think I wrote that this way, determinant of AB, whoops, determinant of AB is equal to the determinant of A times the determinant of B. There's the rule. Okay, I think I'll expand this out. There it is. If A and B are square matrices of the same order, n, then the determinant of their product is the product of their determinants. Okay. There's a little proof there, certainly worth your while probably to go through that proof. Okay. Now, the next theorem I think we can write down too, shows the relationship between the determinant of A and the determinant of C times A. Okay, so let's do this one. Okay, if A is a square matrix of order n and C is a scalar, then the determinant of CA, I'm going to write this like I did before, determinant of C times A is C raised to the nth power. Now I can't do that, I messed that one up. C raised to the nth power times the determinant of A. Okay. All right. So, one thing to remember here, when you multiply a scalar times an entire matrix, now this is not the same as a multiple of a row, the entire matrix. That means every element in that matrix A is multiplied by C. And how many elements are there? N by N. So therefore it is C raised to the nth power. Okay, multiply that by the determinant of A, and that's what you got. So these numbers get very big very quickly. Okay, now we got 2 minutes. Can we do the example 2? I think we can. Let's see if we can. It really turns out being pretty quickly, I think. Here's matrix A. That is, and we're going to do the determinant. Well, let's just do A. That's 10 minus 20, 40. 30, 0, 50. Negative 20, negative 30, 10. All right. Well, guess what? Every entry here is multiplied by 10, so you can take the 10 on the outside and leave you a much simpler matrix. 1, negative 2, 4, 3, if I can read my writing, 0, 5, negative 2, negative 3, 1. Okay? Now, what we want to do is find the determinant of that matrix. Okay? So the determinant of A would be, now remember the rule, whatever that multiple is raised to the nth power, n was 3, so this would be 1,000, 10 to the third, times the determinant of what you have here. And that's 1 minus 2, 4, 1 minus 2, expanding that, 3, 0, 5, 3, 0, and negative 2, negative 3, 1, negative 2, negative 3. Okay, so this will be 1,000 times your down diagonal here. Goodness, my lines are crooked. That's a 0. Down diagonal here would be a 20. 4 times 5 is 20. Down diagonal here would be a minus 36. Okay, let's see if I can erase my construction lines. Pretty ugly construction lines at that. Okay, and the up diagonals here would be a 0. Up diagonal here would be a 15, plus 15, because it was a minus, but up diagonal, and then a plus 6. Okay, so 36 minus 6 would be, or negative 36 plus 6 will be a minus 30, and this will be a plus 35, so that would be 5 times 1,000, which would be 5,000. If I did my math right. Yep, that's what they got. All right, we went 2 minutes over. Sorry about that, but there'll be no extra charge. I think what we'll do next time is begin at the very bottom of that page with those two theorems and make a little conclusion there. And I'll erase the marks I had before. Okay, and let's see, let me get my paper in place. and also do homework exercises here in 3.3. Do any of the odds 1 through 5. They should all be at Calc Chat. Do any of the odds 7 through 13. They should be at Calc Chat. And we'll hold off on those and do the rest of those next time. Okay? Good deal. Any questions, issues, problems, concerns? Okay, I can't remember if I said this before or after James came in, but let me say it again. Please, folks, vote on Tuesday. Okay? We will have class, but if you can't vote any other time than class, go on and vote and then get to class as soon as you can. If you can't get to class, I'll record the class, put it on YouTube video. If something screws up with that, I'll leave the class that I had last summer that's equivalent to this one on YouTube video. But please, people, if you are registered to vote, I hope you are, vote. Now, some of you may have already voted. My wife and I have. If so, come to class, okay? But if not, please vote, okay? Also, please be very careful this weekend. It looks like it might shape up to be a rather pretty weekend. I think it's going to drop in temperature, my wife was saying. So be careful there too. Do not risk the virus. It's out there. Please take care of yourself. We will hope to see you. I'll see all 3 of you hopefully on Monday and then again on Tuesday. So take care of yourself. Any last thoughts, questions, problems? Okay. Then I'm going to quit sharing and I'll end the meeting for us all. So any questions? Take care. See you Monday and Tuesday and Wednesday and Thursday. So take care. Bye-bye.